This video covers work. Work is the scalar dot product of force and displacement. Now, in this equation, you see that my force and my displacement are both in absolute value symbols. So here, we want to make sure that our force is always positive and our displacement is always positive. Now, where we're going to get a negative value is going to come from our theta, and we'll look at examples of that in just a second. Now, work is a scalar quantity, so that's very important. Remember that scalar quantities don't have a direction, so if we do get a negative work, that doesn't mean that it's to the left. It means that work is being done against the system. Again, we'll see examples of that. Again, work is in units of joules, force is units of newtons, displacement is still in meters, and theta is very important, is the angle between the force and the displacement. I can't stress that enough. It is the angle between the force and the displacement, not any old angle that's given to you. So you need to make sure that it is the angle between the force and the displacement. Basically, you want for your force and your displacement to be parallel. And so in order for that to be parallel, that's where the cosine comes in. Now, you can look at this and read it for yourself, but just to go over a couple of very basic examples, here if I have an object being pulled to the right, meaning that my displacement will be to the right, a positive number, and my force is up at an angle, well, I need my force and my displacement to be in the same direction. We want them to be parallel. So instead of using F, I'm going to use F cosine theta and X. So again, my equation is F R cosine theta. So there's two ways you can do this. You can either say my force is F cosine theta times R, and then my angle between this and R would be 0. Therefore, cosine of theta is 1. You can also say that my force is F, my displacement is R, and my cosine is the actual angle given. In the second example, my force and displacement are in the same direction, so I would say F times R times the cosine of 0. Again, if force and displacement are in the same direction, the cosine between them would be 0. For the third example, we have F, we have R, and then the angle between these two would actually be 180 degrees. So that's where my negative is going to come in. This would give me a negative FR, or negative work done. Okay. Again, we'll see what that means in a little bit. Here I have F. Again, my displacement would be in the R direction. It would be to the right. And my angle between my force and my displacement would be 90 degrees. So the cosine of 90 is 0. So I would have no work done by this particular force. So again, these are the most common examples. If we have a positive work done, that means we're adding work to the system. So our object should speed up or gain energy. If we have a negative work, that means we're taking energy away from the system. So it's going to slow down or lose energy. Again, if no work is done, then we should have a constant speed in the direction of motion. We're not adding speed, we're not taking speed away. We're not adding energy, or we're not taking any away. Now, it's possible for any force to do work. The only constraint is that it has to move through some displacement, which is usually the case that normal force does not do work, because it normally doesn't move in that direction. So when you're asking for, or when a problem asks you to solve for the total net work done on a system or an object, then you can simply add all the works done by all the forces involved. Or what you can also do is find the sum of the forces. Remember that these are vectors. So you can find the sum of the force and then multiply by that displacement. In this example, I show how to solve for the net work done on an object. So here, you can see that we're calculating the work done by every object, the work done by a force, the work done by friction, the work done by gravity, and the work done by normal force. And then down here, we have the total net work, and so we're adding all of the works done. And you should see that we should get a 0 joules. On this side, we're using our net force. But again, in this particular situation, it's moving at a constant velocity, meaning all of our forces are balanced, meaning the sum of our forces would be 0. Times 5, which would be our displacement, would still give us a 0 joules here. This is another example of being able to solve work doing two different methods, either using the force that's already parallel to that displacement or using the angle between that force and the displacement. So I showed this in a previous slide. Here we have a force that's 20, a displacement of 10, and the angle between them would be 37 degrees. Or you can say that my force that's parallel to my displacement would be F cosine theta, and then my displacement would be 10, so I still get the same answer either way. In this example, I have a force opposite the direction of my displacement. Now, the important thing to remember is that angles are always measured from 0. So my displacement, which is this one, and my force, which is this one, actually have an angle of 143 in between. So even though a problem gave me an angle of 37, I have to see what angle is actually between my displacement and my force given. So when you are doing this problem to solve for work, you need to make sure you take that into consideration. The other thing you could have done is use the force that is parallel. So that means that we need to find the component in the x direction. And this time we know that it's going to be pointing to the left. It is opposite the direction of my displacement. So F cosine theta would have been the component of F, x. And again, we know it's opposite the direction, so we can go ahead and add that negative or do cosine of 180. Either way would have given you that value. And then we should still get the same 160 that's negative at the very end. Work done by a constant force is the area under the force displacement curve. So if we look at this equation, we can see our base times height. In this particular situation, we have a force that is constant. So the area underneath would give us work. On the right, we see a graph of a variable force. Again, we have a force that varies with position, such as a force of a spring. We know that the force of a spring will increase as the displacement increases. So for this area under a curve, we can use that 1/2 base times height. Or another way to think about it is using the average of your force times your displacement. Now, we covered a little bit of this in class, but in case you have a graph that has a curve, you will most likely have a function that also goes with it. The way we get the area of this is we pretend that we're creating this rectangle, and this rectangle is infinitely small. So in the x direction, we're going to have x. In the y direction, we'll have f. So the area of this particular rectangle would simply have been f times x, our change in x. Now, what it's doing is it's adding up the area of all these infinitely many, infinitely small rectangles from wherever I ask it to begin, which is my initial position, to wherever I wanted to stop adding, my final position in this case. Again, the area under a curve is going to give us work. Here you see another example of force versus displacement. Here we're looking at our force of a spring, which is kx. So we can replace kx where we see force. And again, when we plug that into our equation to solve for the area under this curve, we get that work done by a spring It's very similar to the equation of a potential energy of a spring. Now, before you start writing everything, these are known as work energy theorems. And work is a change in energy. So this piece is important. Now, you notice that on the left-hand side, we do have all our mechanical energies that we've talked about before, and the working or the work formulas that go with them. Now, to solve for the work done by a spring, it is simply the change in potential energy of a spring. The work done by gravity is just a change in gravitational potential energy. And the work done by a force is simply its change in kinetic energy. Now remember that delta does mean final minus initial, so when I write that out completely, our energy at one stretch length minus our energy at our initial stretch length, or our energy at some height minus the energy at our initial height, or our final kinetic energy minus our initial kinetic energy.